Well, I talked about needing error propagation in the past. This is a video on error propagation. So, the general question we're trying to answer with error propagation is, what if you have some quantity like the area that depends on the width and the height? If we happen to know what the uncertainty in the width is, where this delta W, that's a lowercase delta, delta W is the uncertainty in the width, and delta H is the uncertainty in the height. So we've got some width for our object, some height for our object, and we want to find the uncertainty in the area. So we're going to be trying to find delta A. Now, all of this does depend on something called partial derivatives. If it's not something you're all that familiar with yet, don't worry about it overly much. I'll be explaining more or less what I want you to do with it as we go. So in this case, we're going to say that dA is basically the same thing as the uncertainty in A, and there is justification for that. If you really want to fully understand this, I may try and make future videos, but this book right here, Introduction to Error Analysis, ooh, didn't realize it flips it that way. You may have a hard time reading that the way it's flipped. But an Introduction to Error Analysis, you can look for that title and then this picture if you want to get a copy of it. It explains in detail why and how all of this stuff works. Alright, so we want essentially the partial derivative. We'll go back and use the right symbol for this. A is basically the same thing as our uncertainty in A. And it turns out the way it works is if you have something that depends on, like, say, width and height, it's going to be the derivative of A with respect to each one of its variables times the uncertainty in that variable. Oops, dA, dH, and then the uncertainty in H. And it turns out that's pretty much how it always is going to work. So let's talk about this in slightly more familiar terms maybe. If you have a function of several parameters like x, y, and z, then the partial derivative of f would basically be the partial derivative of f with respect to x plus the partial derivative of f with respect to y plus the partial derivative of f with respect to z, each one times dx, dy, and dz. Okay, so that's basically what you need to know. This is essentially what I mean when I say take the partial derivative. And I should have done that first. I think I'm going to probably go through several iterations of this video before I'm finally satisfied with it. But this is the one we're going with for this semester. Alright, so again, if we're thinking about A is equal to the width times the height, that means the uncertainty in A will look like the derivative of A with respect to W times the uncertainty in W plus dA dH with respect to H, and that will look like dA dW. If we take the derivative with respect to W, we're just left with H. Then we've got our uncertainty in W. Then dA with respect to H, that leaves behind the W. We would lose the H. dH, and translating that into our uncertainty view, that would be the idea. Now I will warn you, this tends to be the largest estimate. And frequently, you actually have a distribution that's kind of Gaussian between them. You end up being tighter towards the middle than this would apply, or would imply, which means you'd probably have a better estimate if you added in quadrature. And to add in quadrature, you take each of the terms that would appear in your largest estimate, you square them, you add them together, and you take the square root. So this is usually more realistic. Okay. Oops. So that gives a basic idea how it works. It works on literally anything though. So I'm going to focus primarily here on the best estimate. And I'm going to show a few examples. So let's say we have, let's say we want to find the hypotenuse, and we find the angle, and then we would like to find the opposite and the adjacent sides. So if we look at that, adjacent is equal to the hypotenuse cosine of theta, and the opposite would be equal to the hypotenuse sine of theta. Alright, if we wanted the uncertainty in A, it's going to look like the square root of dA dH with the uncertainty in H squared plus dA d theta with the uncertainty in theta, whole thing squared, take the square root. Alright, if we actually perform those derivatives, if you take the derivative with h, the h just goes away. You're left with cosine theta, uncertainty in the height, or hypotenuse squared, plus, alright, derivative of cosine with respect to theta. So, derivative of sine is cosine, derivative of cosine is minus sine, so we'd have a minus h sine theta, uncertainty in theta, whole thing squared. Now, I will note for all of these, theta must be in radian. Why? Because it's actually a real ratio that represents the angle. 360 degrees is something made up. You may notice your calculator has degree mode and GRA mode. What's GRA mode? Well, it's 400 degrees for a circle. I think it's sometimes used in architecture. I'm not entirely sure on that. It's another way of dividing up a circle. 360 was just convenient because it has lots of factors. So 6s, 2s, 3s, 12s, all sorts of things go into 360. It was very mathematically convenient. It's a very human readable thing, but it's not directly connected back to the reality of a circle, that pi is this special thing that tells you about the ratio of the diameter to the circumference. So this is kind of thinking about sectors of a circle relative to a whole circle, and that's kind of where radians are coming from. So always keep it in radians. Alright, that would actually be our answer here. If we wanted to do the same thing for the uncertainty in O, we'd have dO dH delta H squared, dO d theta, uncertainty in theta squared. And this one's a little bit easier because the derivative of sine theta is simpler to think about. No minus sign. Okay. So this idea just extends however many parameters you have. So far I've done with 2. But you could get a relatively complicated expression for this. To try and give you a bit of an idea for it, let's say, let's relate this back to kinematics for a moment. So I'm going to solve this for v naught. Now, we can actually find the uncertainty in our v naught, where we have x naught, the final position, the initial position, the acceleration and the time, all as variables. So how will that look? Well, the uncertainty in our v naught will be the square root of dv naught dx, uncertainty in x, dv naught dx naught, uncertainty in the initial position x naught, and it just keeps on going. dv naught deacceleration, uncertainty in the acceleration, whole thing squared. Last term we have the time, plus dv naught dt, uncertainty in time and squared. Alright, obviously this is going to get a little bit nasty once we take derivatives. There are several different ways we can write this out that make it a little bit easier. Most important thing to start with, though, is this first term. The t can be treated as constant. We're just taking the derivative with respect to x. The x, therefore, kind of drops out on us. Well, it doesn't drop out on us. So, yeah, this is going to take a minute to do. X over t minus x naught over t minus 1/2 at. If we think about it that way, it'll be easier to see some of these early ones. So the uncertainty in v naught, if we take the derivative with respect to x, notice these last two terms completely disappear for us. They're gone. The first one just becomes a 1 over t. So we'd have a 1 over t uncertainty in position at final. We'll do the same thing. This time we're taking the derivative with respect to x naught. So this first term will go to 0 because it doesn't depend on x naught. The last term will go to 0. It doesn't depend on x naught. The middle one, x naught becomes 1, so we've got a minus 1 over t. And then the uncertainty in the initial position. Oops, forgot the squared on that first one. Alright, looking at, let's see, this next to last one, the acceleration. The first two terms don't depend on acceleration. The 1/2 and the t will survive when we take the derivative, so t minus t over 2, uncertainty and acceleration squared. Last one, every single one of them depends on t. So you'll have to think about what the derivative of each piece would look like. The first two are kind of okay to think about together. For this one, I would suggest kind of mentally rewriting this one as x minus x initial over t minus 1/2 at, because that'll make it easy to think about the parts. So the first one, we basically have x minus x naught times t to the minus 1. So we'll have to take down a minus 1. We'll have our x minus x naught unchanged. It'll become a t to the minus 2. That's the first term there. The second term, we still have our minus 1/2 a. When you take the derivative with respect to t of t, you drop the t. So with a bracket that I'm going to put in a different color, the derivative of this whole thing comes out looking like this, and then we multiply by uncertainty in time and finish up by squaring. Alright, way too much information, I know, but study back through this, understand what's happening with partial derivatives. It's basically, partial derivatives are you take the derivative with respect to one of the parameters, treating all the other parameters as constants, which is why when I take the derivative with respect to position x, I can drop the terms that depend on x naught and acceleration because they don't contain the final position x. So derivative of a constant is 0. Alright, we do have the x over t. Of course, the x, take derivative of x to the first power with respect to x, and you get 1. So make sure you study through this. We're going to start using it relatively soon here. Alright. At this point, I should assign a few practice problems for you to try. I'll try and post up a document with those in shortly. And I'm going to sign off here.